This talk is about our memory leak solution, RESIN, which has been deployed in Azure for 3 years. It has detected, diagnosed, and mitigated for many memory leaks. Cloud infrastructure contains many complex software components, such as host servers, OS kernel, and device drivers. These software run on a massive number of machines with various workloads. Code updates are rapidly integrated, and unavoidably, memory leak bugs will be introduced. In consequence, hosts will slow down, reboot, new VM allocation requests will be denied. The quality of service will be damaged. You may wonder, isn't memory leak already solved the problem? However, this is not the case, at least not the cloud infrastructure. Let me share one real example. On each host, there is a firewall service managing network traffic rules. We call such service a component. During one incident, developers observed the memory usage of the firewall service started to continuously increase on many hosts. On each host, there are massive firewall rule objects leaked. But the testing and the static checker did not find any bug. And some, not all hosts are leaking, which confused developers. So why this issue happened? Actually, this incident has two interesting characteristics. First, it's a cross-component issue. And the problem comes from another service called config agent. It would load the configuration on its startup, then register its rules at firewall service through RPC. When the config agent exits, it is responsible to remove the rules from the firewall service to clean up. However, due to a bug exposed by a new feature, the config agent starts to crash from time to time, causing it exit without cleaning up and leaving the rule object still in remote process. What's worse, the failover mechanism tries to recover the config agent and cause the loop continues, leaking more and more objects. The second characteristic is the crash bug will be triggered when the feature is enabled in the configuration. That's why only some nodes will leak. Such problems are very subtle to troubleshoot. So why detecting memory leak is still a hard problem? Take the firewall case as an example. A common approach is to run static analysis on source code to find leak bugs. Like we said, it cannot find this bug because the leak is triggered from another component. The static approach is ineffective with such cross-component issue. Also, though the approach poses no runtime overhead, but it has scalability and accuracy problem. Oh, sorry, skip. The dynamic approach is more promising, which essentially instrument program and track object lifetime. It both detects the leak and pinpoint what is leaked. But instrumentation adds much overhead. We cannot afford adding such overhead on all hosts. To lower overhead, the scalability is often sacrificed and brings the risk of missing to detect. Practitioners need to make a hard trade-off between accuracy, scalability, and overhead. In Azure, our response to this challenge is RESIN. It achieves a combination of 3 goals altogether. The design of RESIN is based on 2 key insights. First, previous solutions have to make hard trade-offs because they mix detecting a leak and pinpoint what is leaked in one step. Instead, we decompose the problem to multi-stages. First, we perform lightweight detection on all hosts. Then we do more heavy inspection on sampled hosts to confirm and collect evidence, no sacrificing scalability for accuracy. Our second insight is, instead of a team-by-team effort, RESIN takes a centralized approach, supporting all components in cloud with a non-intrusive way, including the operating system kernel. It also gathers information across many hosts to improve accuracy. Here's the overview of RESIN. It has 3 modules. It first collects memory usage data from hosts and generates alerts for leaking components and hosts, and then automatically collects traces for diagnose and analyze. It also automatically mitigates leaking components. For the rest of the talk, we will only talk about detection and diagnose due to time constraints. At the end, we would share the evaluation results. First, we will talk about detection. It has 2 steps. Find a leaking component and find a list of leaking hosts. If a component is leaking, how do we know? A straightforward solution is running anomaly detection for component usage data on each host. This may not work as there are several challenges in cloud to address. First, the cloud environment is highly noisy. Dynamic workloads cause rapid memory usage change and easily create many false positives. Second, many memory leaks are fail-slow faults and could last for days or weeks. It is challenging to capture slow leaks meanwhile raising timely alerts. Also, the cloud scale poses challenges on computation efficiency. It can take more than 1 day to run anomaly detection on data collected from millions of nodes. In response to these challenges, we propose a design called bucket-based PV analysis. Each bucket is a collection of hosts, of which a component's memory usage falls into same range. For example, the first bucket includes hosts running firewall service with usage from 50 megabytes to 100 megabytes. The main idea is, instead of analyzing usage of single process, we focus on the trends of memory usage across all host machines, which makes it can tolerate noise due to workload effect. It is also scalable to large fleet like Azure. Here we just use the firewall service as example, and detecting other components is similar. RESIN first collects usage data from deployed monitoring agent on each host. It then groups the usage data into buckets. It builds a summary table using the most recent time period. By default, it's 15 days. In this way, we can monitor memory change in long range to detect slow leaks. The system runs anomaly detection on the numbers of hosts in each bucket. For each bucket, we use the first 2/3 portion as baseline to build a normal distribution model, and use the remaining data points as a test. If the test data falls into anomaly range, the system will report the component is leaking, as well as the bucket information. In this case, developers of firewall service team will receive alerts. Detecting the leaking component is the first step. We also run a second step that analyzes on which hosts the process are truly leaking. This is important for developers for automation of workloads to collect traces for next step inspection. We propose an algorithm named suspicious window analysis, which scans the usage data changes through time series and estimates the leaking time window and severity score. It outputs a list of suspected leaking process for diagnosis. We omit the algorithm detail in this talk, and welcome to read our paper if you are interested. Only detecting a leak is not enough. Without sufficient evidence and diagnosis support, developers are likely just stuck in confirming and diagnosing the issue. RESIN diagnoses detected leaks for developers. The key questions we answer are, what profiling traces are useful for diagnosis? What is the challenge of collection? And how to analyze collected trace. The trace RESIN collect is heap snapshots. It would first enable tracing of Windows heap manager on a process and start to periodically take snapshots. It would wait for a new leaking allocation happens again. Take the snapshot and compare the snapshot before and after the leak allocation. Then we get the stack traces of functions that allocates the leaking objects. A key challenge of this approach is a leak allocation should accurately trigger the collection to finish. A simple solution is we set a hard memory threshold and trigger completion when the threshold hits. But it can close up collection too early when a spike caused by normal workloads happens. Our solution is pattern-based strategy. We observe that a leak is often repetitive and shows a consistent pattern across time, such as stair or spike. Their unique characteristics can be learned from historical usage data, and we classify leaks based on parameters. Then we use corresponding strategy to monitor the memory usage changes. For example, our tool will try to complete profiling at points A, B, C. not D, where noise instead of leaks happen. Depending on case, the collection process can take hours to 1 day. The last step is to analyze the collected snapshots to output the root cause stack traces. The challenge is to handle many noisy allocation and localize the true buggy allocation. First, the diagnosis engine will differentiate the snapshot before and after the leak, and identical stack traces that contain new allocation. And then it will rank this allocation based on their allocated object sizes. It will use the characteristic learned in the pattern recognition step and estimate the leak object size. Prioritize allocation that are closer to the estimation. But a list may still contain many noisy stack traces. Developers cannot afford to check them all. How do we filter them? Our solution is to collect reference snapshots. Besides taking heap snapshots of leaking process, RESIN performs a fingerprinting step that takes heap snapshots of non-leaking processes to build a reference database. Non-leaking nodes are determined by calculated severity score. Reference snapshots provide a list of common noisy stack traces, and we can use it to filter stacks from normal workloads. At the end, send the diagnosis report to developers. For firewall example, the leaked object comes from add-rule function, and that is a pinpoint. Now, evaluation. RESIN has been deployed in Azure production since late 2018, covering millions of hosts, hundreds of different components, and deal with massive data daily. In the evaluation, we aim to answer questions such as how effective is RESIN in addressing memory leaks in Azure, and how accurate is detection. We collect data for 14 months and analyze. During this period, RESIN in total detects 564 leaking cases and reports to developers. The ticket tracking system does not enforce the response, so not all cases will be marked as resolved in the end. Sometimes developers may take actions, but not take recorded results. Also, RESIN detects many leaks at very early stage, so developers may not record as serious incidents. In total, we collect the result for 291 cases. The two most important metrics to show host memory leak impact are VM reboots caused by low memory and new VM allocation errors caused by low memory. The improvements brought by RESIN is significant. The VM reboot is reduced by 41 times, and allocation error rates are reduced by 1 magnitude. During the evaluated period, RESIN incurred 7 false positives out of 291 resolved cases, mostly due to the developers adding a new memory-consuming feature or configuration change. It missed only 4 cases, in which developers detect them faster by manually monitoring cluster after adding code changes. We also evaluate how useful the diagnosis result is. RESIN in total collects and generates reports for 157 cases. We cooperate with developer teams to debug 14 cases among them. In 11 out of 14 cases, the diagnosis result directly pinpoint the root cause function. The pinpointed function is usually close to the fix. For missed 3 cases, developers either found memory dump more directly useful, or they collect more useful traits on their private testing cluster. We use the firewall example at the beginning of this talk to show the usefulness of diagnosis results. After detecting the leak, RESIN collects the snapshot traces and analyze and pinpoint the add rule function to developers. Developers did not find a bug in this specific function first, but the report prompted them to check the firewall rule list on these machines. Then they found the rule list on this machine have been flooded with not released rules. They are coming from crashing config agent service. Eventually, they found the root cause. To evaluate the trace collection overhead, we collect 1 month's data from 2021 and found only around 300 nodes are collected with traces at least once, which is less than 0.1% of all nodes in the cluster. On this host, only 9% of VM deployments are affected by tracing requests. Enabling tracing slightly increases average memory usage and cause CPU usage spike for a few seconds. The median of end-to-end VM deployments increased for 1 second. Overall, the costs are acceptable in production deployment. So a quick summary of this talk. We present RESIN, an end-to-end service designed to tackle memory leaks in production cloud infrastructure. It takes a divide and conquer approach to decompose the memory leak problem. And we design a multi-level solution with novel algorithm. RESIN has been running in Azure for more than 3 years and successfully reduced low memory-induced VM reboots and new VM allocation errors. Thank you, and now I'm open to questions.